Hello, I wrote some code for Arduino recently to control stepper motors, and it turned out to work fairly well, so I thought I'd make a little video and explain a little bit about it and put the code up just in case people wanted to try it out. So the goal for this exercise was to control multiple stepper motors and have them move in a coordinated fashion. So for example, if we have one motor here that needs to move 90 degrees and another motor that needs to move 360 degrees, even though if they did that individually they'd take different times, when they do it coordinated they both start and stop at the same time. So that's one goal. Another goal was to have the movement accelerating and decelerating, so instead of just jerking into motion and keeping a constant speed and then suddenly slamming to a stop, it would start and ramp up the speed a little bit more gradually and then ramp it down at the end when it came to a stop. So that was another goal. I wanted to do this for 6 motors, which is what I've tried it with, and it seems to work pretty well with 6. It could work with more, although I think you'll find that the movement will start to get a little bit scratchy, not quite as smooth as it would with less motors. And another goal was to do this in an interrupt routine so that the main program of the Arduino could keep going doing other things while the steppers were moving. So that was the goals. Seems to be working all right. Now I have to admit I didn't check if there were any other stepper libraries out there that can do all of that stuff. There probably are, and they're probably better implemented than what I've done, but I just kind of wanted to try making one myself. So don't take this as an attempt to make a better wheel or anything like that. It was just sort of for my personal amusement, I guess. So in this video I'm going to explain some of the steps or the progress that I went through while I was working on this, and it's going to start off pretty simple and get quite complex. And at the beginning of the video I will explain the simple bits because that sort of explains why it needs to get complex later on. But as it gets more and more complex I'm going to explain less and less of it. Obviously otherwise the video would just be incredibly boring. And I think that people who have the aptitude to follow this further will no doubt look into the code themselves anyway, and maybe you can ask me if there's any specific details that you want to know a little bit more about. So these stepper motors have 4 wires here, and depending on which way the current is flowing in and out of those wires will the motor will either be stepping or it'll be sort of part way between steps and so on. But managing this stuff here is pretty complicated, and to be honest, if I had to do that I wouldn't have even bothered doing this. But what I'm using is these A4988 stepper drivers, and they make everything quite a bit easier because all we have to do, we really only need to control 2 pins. So we have this direction pin, and whether that's high or low will determine which direction the motor will turn, and then there's a step pin there, and you just take that high and low to make the motor step. I think it's when it senses this pin going high it will step, but you obviously have to take it low after that before the next step to make it go high again. See what I mean? And then we have this enable pin on there as well, and you don't actually need to control this one. You can hold it high. Is it high or low? I'm not sure. Hold it either high or low to enable the motor, but the point is that you don't actually need to have any intelligent signal on there. You can just connect this to high or low, or whichever it is to make it work. I'm not sure. Anyway, the point is that you only need 2 pins per stepper motor to make this work, which is pretty cool, because that means that even something like this Arduino Uno could handle 6 motors if you wanted it to. Of course you need 6 of these drivers to do that. So to start off with, I'm just going to look at controlling 1 stepper motor because that will get a lot of the main concepts out of the way. And on here I have some wires connected to digital pins 2, 3 and 4, and they are going to be the direction, step and enable respectively. And let me just get that connected up. Let's have a look at what is probably the simplest program that you can write to control one of these stepper motors. I have defined the pins that I'm using there, so this is just digital pins 2, 3 and 4 as I mentioned before, and I've set those to be outputs, and then I'm taking step pin, which is 3, I'm taking that high and low, and then I'm waiting for 10 milliseconds between pulses. Now this delay, or the interval between pulses, will define the speed of the motor. Now this is actually running at the moment, so I'll just have this little switch here that I'm using to turn the battery off and on so that I don't have it running all the time. But that's what this program does. So this is with 10 milliseconds between steps. And if I take it down to just 1 millisecond between steps, it gets predictably about 10 times faster. So the speed of movement, as you can see, is inversely proportional to the delay between the steps. That's kind of the point that I wanted to look at here. Let me just turn that off. By the way, the enable pin does have to be held low to enable the motor, not high. I just checked that before, and I realized that I don't have that in any of my examples that I'm about to look at, but what I should be doing is something like this at the beginning of each sketch would be better, just to make sure that it's going to work. Here's another sketch which is very similar to the one that we just looked at, except instead of letting it run continuously, we have a function which is going to take a number of steps to move by, and then we use that to loop over this step high and low thing that we were doing before until it's reached the required number of steps, and then it will just stop. And we're also using the direction pin. We're setting that to either low or high depending on which direction we want the motor to turn. And I've got a couple of examples here. I'm going to step 800 steps. Now this motor is a 200 steps per revolution motor. So normally 200 steps would be a full revolution, but in the stepper driver I have it set to quarter stepping. So it's actually going to take 800 steps to do a full revolution. So if we look at the tip of the pointer, this orange thing there, you can see that it's lining up pretty much right on that intersection in the lines of the grid on the table. So if I just turn this on and reset the Arduino to run this, we'll see it goes right back to where it started. And the speed is pretty similar to what we had before when we were doing 1 millisecond delay. So again, this interval that we have between steps is going to determine how fast it goes. So to make it faster, I can make this number smaller, right? But we are not doing any acceleration yet, so let me just run that again just in case it wasn't clear. It's not speeding up and slowing down, it's just immediately jumping to that 1200 speed. So that's a bit of a problem because jumping from motionless to a speed requires a certain amount of energy, and if we take this down, I think 400 should still be okay. Let's try 400. So it's 3 times faster. You could see it sort of jerking the motor a little bit there because of that inertia, that it's that instantaneous speed that it's trying to do. And I think I might be able to get it to go twice as fast as that again. I'll just hold the motor this time. No, I can't. So this is where we start to strike problems. Even though I know this motor can go that fast, it cannot accelerate that fast. So there's a difference between top speed and the highest acceleration that it can manage. So the point of doing acceleration is to, instead of just immediately jumping to that speed, we want to gradually work our way up to that speed, and I'm pretty sure I could even get it to do stepping at intervals of 100 microseconds like that, once we get the acceleration sorted out. Now let's have a look at a basic, rather naive form of acceleration. This is not really what we want, but it should illustrate how even a rudimentary kind of acceleration can help get us past some of the problems that we just saw. So in the loop function we have kind of the same thing as what we just had, except for this time we're going to be turning 2400 steps, which is 3 full rotations in each direction, and we're using this function called simple acceleration. So all that simple acceleration does is it says there's a low speed that we're going to start at. We want to work towards a high speed, but we can't do it immediately. So we're going to start at an interval of 2000 microseconds, and we're going to work towards a high speed of 100 microseconds, which is what we tried to do before, but it couldn't do it because it was missing steps. And with every step that we take, we're going to change this by 2 microseconds. So the first step will take, the interval will be 2000, the next step will be 1998, then the next one will be 1996, and so on, until we get to the top speed of 100. And then we'll hold it at 100 until we get towards the end of the movement, and then we'll have to slow down again. So it will go from 100 to 102, 104, and so on back up to, hopefully it'll be right about 2000 just before it stops moving. So to calculate the points where we need to stop this ramping up behavior, we can take the total or the difference between those two speeds and divide that by how much we're going to change each step, and that will get us that will let us know how many steps that we need to take for that ramping up portion of the movement, and then the ramping down portion will be the same number of steps at the end. So in my code, I'm not doing any different lengths of ramping up and down. The acceleration at the start and the acceleration at the end, or the deceleration if you like, are going to be the same sort of acceleration. So then we have this value d, which we start off as our low speed. Now of course these numbers are kind of backwards. Low speed is high number and high speed is a low number because this is the interval. Just keep that in mind. So d is going to start off at the low speed, and then we're going to do that step pin high low, and then we're going to wait for the duration. Then we're going to check if we are currently before the point where we have to stop ramping up, and if we are, then we'll decrease the interval or the delay by that change value there. Otherwise, if we are on the ramp down section, then we'll increase the delay to slow down. Otherwise we do nothing. So if we're in the portion of the movement where we are neither ramping up or down, we're at full speed, then we just leave D as it is. Anyway, enough talk. Let's see what this does. So it goes back to the point there where it should, and it starts off moving slowly and then it goes faster. And that fast point in between is actually at 100 microseconds per step. So we can manage to do that without losing steps, and we get back to where we should be. So that's not a bad first start, and it might be kind of okay for some purposes. But if you listen to this, if you listen to that sound, hopefully you can hear that kind of. It's not a natural sounding acceleration curve. And the reason behind that is if we graph what's going on here, so the first step, the duration or the interval or the delay is 1000 microseconds. For this example here, excuse me, I had 2100 there, but just for this graphing example I'm starting from 1000 and I'm decreasing in steps of 4, so it's 996, 992 and so on, just so that we don't have too many values to graph. But here this is the delay, I guess you could say, and this is the speed that results from that. And to calculate the speed, I've just divided that, or it's just the inverse of that, so it's 1 over 1000 to get that number, 1 over 996 to get that number, and so on. And then if I graph this speed by, oops, not sure why those are down there, but this is the portion that I wanted to graph when we get to 100. Now you can see that that is not a linear ramping up of the speed. It's sort of a exponential curve almost, so that we start off and we're going quite slow for quite a long time, and then all of a sudden right at the end we do most of the increase in speed all within a very short space of time. So this is not a natural way to ramp up the speed. Ideally what we want is a straight line that just goes from this point straight up to there like that, and the speed will increase linearly. But how to calculate that is a bit of a tricky thing, because this side is what we're actually inputting. So how to get this as a reciprocal of that and still be linear is the tricky thing, which led me to a little bit of investigation. And my investigation pretty much ended when I came across this document, which explains everything quite well and included all of the info that I needed to use or needed to know. It has some source code which I couldn't really make head nor tail of, but that's okay because I was trying to write my own anyway. But regarding what I was just saying before about a linear speed ramp, the graphs here, this is acceleration, so the W is rotational speed. Oh, it says it up there. This is acceleration. So what we're looking for is a constant acceleration, which will result in a linear speed increase like that. So we're going to linearly increase the speed, hold it constant for some duration, and then ramp down again. And what I was saying before is the ramp up time and ramp down time for what I made will be the same. So in this graph, it takes longer to ramp up than it does to decelerate. So the code that I wrote does not do that. It's going to be symmetrical. And this is the position. It's sort of a smoother position change. And when we listen to the movement in a minute, you'll see that it sounds much more natural too. So this document, if I just look a little bit further down here, I'll try and speed this up a little bit. But basically, everything is explained in detail in the appendix as it says there, and I'm pleased to say that I could actually follow every single thing that was in the appendix, which is, I think, a first for me. Actually, when I look at these sort of white paper documents, usually they lose me after the first few lines of equations and stuff, but this one was not too bad. And the way it works is we need to know how to calculate the time delay for each interval between steps based on the previous time delay. And the way that we do that is we have a starting delay, and in my code just before I picked something like 2000. So this is kind of what we're going to start off with, our first delay. And they have formulated this like using these variables here, because what they're trying to do is put in some numbers to get an exact degrees per second speed. And I have not worried about that, because what I'm going to do is I'm just going to put some numbers in, or put a number in for this, look at what kind of speed it gives me, and then adjust it and make it fit whatever I want it to be, without knowing that it's going to be X degrees per second when I put these numbers in here. So that's another thing I should mention about my library. I called it a library, didn't I? My code. You will not be able to get an exact specific degrees per second speed from your steppers. You'll just have to adjust these numbers to suit. So for my purposes, I'm just going to use a constant for this. Now, this next one here is really the meat of the whole thing. This stands for the delay at step n, and that is based on the delay in the first step multiplied by this little thing here, and n being the number of steps, so the nth step this is. And as they say here, the computational power of a microcontroller is limited. Calculating these two square roots is time consuming. So they have used a less computationally complex approximation using the Taylor series for that, to basically do the same thing without using square roots. It's not as exact, of course, but that's perfectly fine. Actually, I have to admit I didn't follow the Taylor series part, because I kind of missed, or I must have been sleeping when they did that at university, but I heard of it. I know what it does, but I don't know how to do it. So anyway, when you want to write this in code in a weaker CPU, like one that doesn't have a floating point unit and so on, you're going to do something like this. You'll take the previous delay, which for the first step will be that delay there, and then you'll do this, so 2 times the previous one. Well, you can see it right there. And the point is that this is much faster than the double square root. It does increase a little bit of error, which I haven't bothered about. I just sort of let it run, and it works perfectly well for what I'm trying to do. So for my first attempt at using this method, I just used this formula to fill an array with the delay intervals that I needed, and then I just ran through that array forwards and backwards to do the stepping. So I'll just look at this one quickly. We do the same thing. We do forwards and then backwards for the directions, and then the function that I've written, you'll notice I'm not passing a number of steps to do here, because I've just made it a little bit simple, and I have used a fixed number of steps. So that's 400 steps, or 400 array values, because this is where the array is declared, where we're using that number of integers. Now some of these things here, angle, acceleration, and so on, these are the things that I initially started using from this formula, and then this C0 is going to be that there, and you'll see that I've used all that stuff there. But in later versions of the sketches, I've just replaced this with a constant number like that, or whatever it is. And again, we have a high speed of 100 there. So all this does is it runs through that array and uses this formula to put numbers for the delays in that array, and then it runs through that array forwards, doing the stepping, and then backwards. And because there are 400 steps or 400 values in that array, we're going to get a total of 800 steps. So again, it's going to do one full turn in each direction. But this time when we listen to this, you should hopefully be able to tell that it sounds a lot more natural when it moves. So let's run that. So it's a bit more of a smooth sounding motion. So that works okay, but obviously filling a fixed length array with the interval values is not very practical for the general case, and I also wanted to have this running in an interrupt routine instead of taking up the main code path of the program. So that's what I did next, and this is where it starts to get a little bit complicated. If you're familiar with interrupt routines, maybe not so complicated for you, but it's quite a big change, and the sketch suddenly gets quite a bit bigger, and probably this is the last one that I'll explain in any great detail. But anyway, starting from the top, we have the same stuff that we had there. I've defined a macro here so that we can use port manipulation rather than using digital write to take the step pin high and low. It just makes it a little bit faster. So this macro will do what it says it will do. There's just another convenience macro to turn timer interrupts on and off. Then we do kind of the similar thing that we did before, except we have to do a little bit of extra setup to say what kind of timer we want to use here. So I'm going to be doing the compare to counter style timing, so that whenever the timer 1 gets to this value here, I forget what these are called, but whenever timer 1 gets to, or timer counter there, gets to that value, the interrupt routine will trigger and run. And this is the point where I stopped using this calculated version for the acceleration. Well, essentially this is the acceleration, but you could also think of it as the slowest step that the motor will do when it starts. So 1600 microseconds is going to be my C0 for this case. Now down here we have the interrupt service routine itself, which I'll look at in a second. But in order to make that work, we need to have a bunch of variables that are going to be looked at by the interrupt routine and by the main code as well. And it seems like they need to be volatile for the most part. I've made pretty much all of them volatile. Not sure if that was entirely necessary, but I was having a lot of problems at some point, so I made them all volatile, and it's been working okay, so I just left them like that. So this is mostly quite a bit of housekeeping that goes on inside the interrupt service routine. Direction is going to be, I think, 1 or -1 depending on which way you want the motor to go. Max speed is 20 here, so this is the number of microseconds that the program will wait before triggering the next step. Now you might think 20 is very, very small compared to those ones that we just saw before, because we were having trouble making it even do 100 microsecond pause before. So how can we make it 20 now? That's going to be much shorter. And the answer is that some of the time is taken up in running this interrupt routine itself. So it's not just 20 microseconds, it's 20 microseconds plus however many ticks it takes to do this. Oh, and that's the other thing. It's not microseconds, it's timer ticks too. That's yeah, that's true. So we're talking about a totally different measurement of time here now. Anyway, so there's a bunch of variables here, and we're keeping track of how many steps we've done so far. Total steps, what? Step count? Total steps necessary, I think that is. And also the position of the motor. So if it starts here, we call that 0, and then we turn 500 steps. We know we've turned 500 steps, and we know where to go to get back to 0. So it's just sort of keeps track of the absolute position of the motor. And then we have a variable we've set that to true when the movement is finished, so that the main program will know that the motion has been completed. Anyway, inside the interrupt routine, first thing we do is check if the number of steps we have done is enough to finish. And if it's not, in other words, the step count is less than the total steps, we need to keep stepping. So we do step high, step low, increase the number of steps, and we also increment the step position to keep track of where we are in absolute position. Otherwise, in other words, we've moved far enough, we've done enough steps, then we set that movement done value to true and turn timer interrupts off so that this interrupt routine is not going to be called anymore after that. And then we do a similar thing to what we just looked at. We need to figure out if we are still in the ramping up phase or not. And I've determined that just by having this ramp up step count value set to be 0 or not. So it starts off as 0, and as long as it's 0, we're still ramping up. So increment the step number, and then we do this thing that we were just looking at there, this one. So this is D in my code. So that's it there. So basically we're using the D, or the delay of the previous step, to determine what the delay for the next step is based on this N, which is the step number. And then if we are still less than the maximum speed, if we have reached the maximum speed, then we set this ramp up step count. So this value now will no longer be 0, so next time we're not going to come into here. The other condition that we should check is if it's a very short movement, we might not have enough time to reach the maximum speed before we need to start slowing down again. So that's what this next check does. If we've done enough steps to get halfway, basically that's what that says, then in that case also we will say that the number of steps in the ramping is going to be however many we've just done. And then in the ramp down phase, we need to do the reverse of that. So we decrement N, and then I calculated with a pen and paper, this formula here is basically the inverse of that. So I basically solved this equation for C n minus 1, and that will allow us to step downwards, if you like, down that ramp. It's not precise, but it doesn't really matter. And then at the end of all that, we set the timer counter, what is this called? The compare register, I think it's called, something like that. We set that to whatever the interval we want to wait for until the next time we come into this interrupt. So it's pretty tricky. The tricky thing about trying to make a video like this is if people understand how these interrupt service routines work, it doesn't really require a whole lot of explaining. But if you don't know how they work, then what I just said probably wouldn't make any sense to you. Anyway, so a little bit further down here we have a function called move n steps. This time we are actually taking a parameter to move a certain number of steps. So we just do a bit of housekeeping again. We set some initial values before the move starts. D is going to start off at the C0 that we just set as some value there, 1600, my slowest step delay. Bunch of values have to go to 0, like that. Movement done is false, and then we turn timer interrupts on so that interrupt service routine will start being called. And then, since we have a value called step position, which we're keeping track of the absolute position of the motor, we can also make a convenience function like this. I should really call this move to absolute position. That would be a little bit better name. But it's just a helper function to let you get back to 0, I guess, is probably when is most useful. Anyway, and then in the loop here I've just got a bunch of examples where this is just calling over and over to do some movements. Towards the end I've set the max speed to 600, which slows it down quite a lot because it was 20 or something before there. And again, this is not microseconds anymore, this is ticks. And then 400 makes it a little bit faster, 200 makes it a little bit faster again, and then finally 10 makes it really fast, and we should move back to position 0, so we should get back to exactly, again, let me just line that up. Oops. So it's going to be on that corner of the cell on the graph on the desk with a bit of luck. So let's turn this on and run it. That's the slow ones. Oops, it just moved a bit. It just moved a little bit at the end there, but but you can see that it's keeping track of all the steps properly, and it's moving pretty fast. I mean, could go faster. Let me just make it go a little bit faster so we can watch that again. Because we're accelerating now, we can set this max speed to be quite fast, and we shouldn't lose track of it. Just get my fingers out of the way. But I'm really hoping you can hear this, because looking at it doesn't really show you too well what's going on, but the sound really gives it away. Anyway, hopefully you can hear that it's accelerating quite nicely. So some of you may be thinking, what on earth was the point of all that complexity just to do basically what we were doing already before? Well, the advantage of doing something in an interrupt routine like that is that it lets the main part of the program continue doing something else while the stepper is turning. So if we have a little bit of a look at this move to position function that I was using to do all those movements, there's actually a line in here if we pass, or well, the default parameter here is true, so if we give no second parameter, it will come in here and it will just wait until that movement done value goes true from up there before continuing. But we could issue this move to position command and then just keep going here doing something else. So let me just illustrate that with another sketch there. So this is the same sketch that we just looked at. I'll better just upload it. Except, okay, so you can see it's moving 8,000 steps, which is 10 revolutions. Hold on. And I just wanted to, now let me just reset this Arduino again. Now notice that it says starting and finished at the same time. That's because this starting command happened, then this one happened, then this one happened, all pretty much at about the same time. So the program here is able to continue doing whatever it wants to while the interrupt routine is also running kind of at the same time. And I have a couple of other illustrations which might help to show this a little bit more interesting way. So let's say we have a value called count, and we want to do something while this movement done value is still false. So we can print out the value of count and increment it and then wait half a second. And I'll just put this over here. So let's run that. So you can see that value is being printed out there. So it's again not a very exciting example, but another very important thing that it lets us do is if we wanted to stop that movement halfway through for some reason, I'll just paste this in. So let's say, look, we got up to 5 there, but let's say we wanted to stop it when the count gets to 3. So this, in reality, this might be a user input, like there's some kind of a button that the user can push to stop the motors turning if they see something's going wrong or whatever. So let's try that. There's a little bit of a delay there because it gets to do one more iteration of this loop before it stops. But the point is it didn't get all the way through, and if we were to print out how far it got, step position, isn't it? Yeah. Actually, we can print that out while we're moving too. Let's try that. Print. This might be a better illustration. Let's try that. Yeah, try that. Okay, so even though we told it to move 8,000 steps, we're also able to run other jobs concurrently and interrupt it while it's working. So those are the main points that we gain by doing things in an interrupt routine like that. So the next step in this whole procedure is to Did I just hear somebody yawning? Could have sworn I heard one of you guys yawning out there. Hang in there. We're about to get to the good stuff. So the next step is to, of course, do this with multiple stepper motors. That was part of the goal. So I can't use just the single driver board thing here. I'm now using an Arduino Mega underneath there, and it has this shield thing on it, which is mainly used for 3D printers, I think, but not necessarily the only thing it can do. But it only has 5 of those drivers on, so I do actually have to use this single board on these auxiliary pins here, but it works perfectly well, no trouble with it. The sketch for this is going to change a lot, and this is the point where I'm not really going to explain too much of it. Hopefully people who are interested in this will be able to follow it a little bit further themselves. Otherwise, just let me know if there's something in here which is a bit strange, but I'll just quickly go over I'll just go over the pertinent points of it that were different from before. So obviously we have a lot more pins to deal with, but basically the same way we deal with them. We deal with them the same way as before. Major change is that now that we have multiple stepper motors, we need to keep a set of these housekeeping values, like what step we're up to in each one, the delay value, step count, total steps, all that kind of stuff. And each motor needs to have its own set of these values. So I've put that into a struct, and I'm keeping an array of 6 of these structures to check, or to anywhere in the program that needs to deal with the step motors, we'll use one of these structures. And probably just skip over most of this. It is quite a bit longer. So here is, hold on a second. So we have an array of steppers there. So anytime we see steppers, that's what we're dealing with. So down here we have the first stepper motor, and we are setting a function which will tell it which pin to use to change the direction, and this function tells it which pins to use when stepping. So that'll be one of these. For example, it's that one there, like that. And the structure has a function pointer to store that, so that's why we are assigning a function to that value there. And then we have values also for the acceleration. So this is basically determining how fast it starts out at and how fast it accelerates. And then this value is obviously the top speed, or now called the minimum step interval. So I've tried to give things a little bit more relevant names at this point. So we do that for each motor as we see fit. And then there's a whole bunch of stuff which I'll probably not look at too much. But one main thing we need to do is, when we are setting the time for the interrupt to trigger, we need to figure out which motor it's going to trigger for. Because we have 6 motors and we can only trigger one step in the next interrupt. So that's what this function does. And then in the interrupt service routine itself, we know one of the steppers is triggered, and we need to figure out which one it is. So we've got to do all this kind of stuff in here and figure out which one it is. And I'm using this value, remaining steppers flag. This is a bit flag to keep track of which steppers have yet to finish their movement. So there'll be a bit set in that value for each motor that's still moving. And yeah, let's just skip over this, eh? You want to look at it working, right? Yeah, let's just look at it working. So that's that whole sequence there that we can see all of this stuff just finished. So it's pretty quick. And you can see that the motors are all moving. They're not coordinated yet, but the reason they look like they're coordinated is because if we look up here, I have the same acceleration and top speed set for all of them. So it's 1050 all the way down. So let's just run that one more time. And you can see when they move together, they're all moving at the same speed. So it looks like they're coordinated. But if we change let's change the top speed for a couple of them. This should be a couple of the ones in the bottom row. And one of the ones in the top row, I think this is the middle one in the top row, I'll make that start off slower. Alright, so let me run that. Now we should see that they're not coordinated anymore. Okay, so hopefully you could see that that one and that one and that one were slower than the others. And this one is the slowest because we set that one's maximum speed to, oh, is it that one? Must be that one there, 450. Anyway, so they're not coordinated, but they do work together or move together quite nicely. So basically the only step left to get them coordinated is to figure out which one is the slowest and how long the slowest one is going to take to finish. Well, it's not necessarily which one is the slowest, because it also depends how far you're telling them to move, because each motor might have to move a different distance. So it's how long it's going to take to finish. Which one is the slowest one to finish? That's what we want to find out. And then we want to just slow all the other ones down by whatever factor they need to finish in that same time as well. And I'm not going to explain that sketch, but I'll just load it up and run it for you. Alright, here is that sketch. This is the last one, I promise. And it just has an extra step in it before it gets to actually doing the movement, and that is to adjust the speed scales. So in that structure where we have all those values stored for each stepper motor, there is an extra value called speed scale, and if this value is 1, it's just going to move at the normal speed. If it's less than 1, it's going to slow itself down to match the speed of one of the slower motors, and this function will calculate that before each movement. Now unfortunately I've used a very slow brute force method to calculate how long the motors are going to turn, so I'm still sort of in the process of trying to improve that. But let me just run this and you'll probably see what I mean. In between each individual movement there's a pause of about a quarter of a second, or maybe not that long, but there's a slight pause that we'll see, and that is probably going to be gotten rid of soon, sometime. See how there's a pause between each? But now those movements are all coordinated, so even though some are moving a lot, like that one was moving like 10 revolutions, some of these other ones were just moving 1, I think. But whatever distance or whatever time it takes them to move, they're all matched. You should be able to see that. By the way, just in case it's not clear why we might want to have a coordinated movement like that, suppose that one of those motors is controlling the x-axis of a CNC machine horizontally, and another motor is controlling the y-axis vertically like that, and we want to move the spindle between these two positions there and there. If both of those motors were allowed to move at the same speed, the path that the spindle would take would be, first it would go down here like that, because both motors moving at the same speed would make it diagonal movement like that, and then the Y movement is finished but the X needs to keep going, so it would move like that. That might be okay, but if you want it to move in a straight line directly between these 2 points, you'd have to slow down the Y motor to 1/3 of the speed of the X motor in this case, because there's 3 times as much distance to travel in the X distance. So if you did that correctly, then the spindle would actually go like this in a straight line between those 2 points. Just put a little delay in there because it wasn't too obvious what's happening. Let's put a 1 second delay in the middle of those 2 coordinated movements. And I don't have many examples here because it's kind of a pain in the butt. You can't really put it in a loop. You just sort of have to type them out by hand to have some interesting movements to look at. But let's just run that again. So it's working quite nicely. Still some improvements to be made though, but I'll put my code up on the website for those who want to look at it. And if somebody can help me with one of these questions that I had, actually that's an idea. Maybe I can ask for a bit of help from you on this. If you're still watching this, obviously you are interested. Whether you'll be able to solve this for me or not is a different story. But this is the function that I'm using to estimate the time that it will take for, well, I'm calling it acceleration. Yeah, acceleration. So basically, all I'm doing is looping through a certain number of steps because we know how many steps it's going to take. But what we want to know is the total duration that will take. And the duration is the sum of every value along this series. So the way I'm doing it is I just do that for n times by just repeating this over and over and over and adding the value at each point. So I think if you were to write that out formulaically or a little bit in mathematical notation, it would be sigma, like that big sigma sum of all of those values from n being 0 up to k or whatever. I think would be something like that. I haven't really tried to figure that out yet, but that's probably the next thing that I need to do to make this a little bit more professional or to get rid of this brute force calculation at least. So if you know how to do that, let me know. In the meantime, I'll try and figure it out myself because there's got to be a better way to do it than this nasty brute force thing that slows it all down. Anyway, that is the end of this video at last. I'll just let you watch that one more time because it's kind of cool. I think it's cool. Spent so bloody long making it, I'm going to watch it.